So linearization is just using the tangent line to approximate the value of a function for something that we might not be able to approximate otherwise. So we usually use capital L of x as the linearization function, which is our approximation for f of x. The point that we're going to center our approximation at is the a value, and that a value is just a value of the function that we know. So if we were looking for the square root of 101, we'd use an a value of 100 because we know what the square root of 100 is, and we could then use the tangent line to the square root function to approximate the value of the square root of 101. That sound good? Everybody remember that? Familiar from last year a little bit? Hopefully. If not, it'll all make sense soon. So our linearization function is the value of our function at a, so the value of our function that we know how to easily evaluate, plus the derivative of our function at a times x minus a. And then we'll determine the accuracy of our approximation just by using a calculator. So you're going to want your calculator with you today. And we'll do the absolute value of the actual value at a minus our linearization function at a. No, I don't know why I wrote a's there. Those should be x's. But yeah, f of x minus L of x. I don't know why I put a's there. Good or no? Yes, no, maybe. Good. Good. All right. Spectacular. All right. So we're going to use linearization to approximate the square root of 26. So what is the specific function that we're going to be using? What's our f of x function here? Should be f of x is, good, somebody said something here in the chat. Hopefully it's the right thing. Yeah, square root of x, good. So f of x is going to be the square root of x. And what is our a value that we're going to center our approximation at? Should be 25, right? Because we know what the square root of 25 is. And so we'll just go in and use that formula. Our linearization at 26 should be equal to f of 25. And then what? What's our formula say? We got plus f prime of a times x minus a. Right? So plus, what's the derivative of f of x? 1 over 2 root x. And that's at 25 times our x value, which is 26, minus our a value, which is 25. Good or no? Hopefully that's all right. So what's f of 25? What's the square root of 25? Should be 5. And then plus 1 over 2 times 5. So 5 plus a tenth, or 5.1. And you probably remember last year I was like, that doesn't seem like that great of an approximation for the square root of 26. Like I could have just guessed, oh yeah, maybe it's 5.1. But then when you actually plug it into your calculator, what is the value that you get? Yeah, 5.099. So give me like a full decimal on that. 5. Every time I click on the screen, the chat goes away and I can't see what you guys have written. All right, 5.099. What was it? 019. 4. Yeah. And so if we want to find the accuracy, we'll take that actual value and we'll subtract the value that we got, 5.1, we'll take the absolute value of it. And I believe that comes out to be, I don't know, something like 9.805. 805? No, that's not right. Times 10 to the negative 4. Is that what you guys got? No? Maybe? Yeah? Yeah? All right, perfect. So when we talk about accuracy, we will drop this down to 1 degree less than this, sort of 1 degree more than this. So we'll say that this has accuracy of 10 to the negative 3 accuracy. So basically what that's saying is that our answer is within 10 to the negative 3 of being correct. So it's within, 1/1000th of the right answer. Does that make sense? Good or no? Yeah? Yeah, 1 degree greater. That's correct, Nick. So we're off by 9.805 times 10 to the negative 4, which means that we have accuracy to the degree of 1/1000th, 10 to the negative 3rd power. What if you were off by exactly 1/10,000th? Then you would say that if it was exactly 1, we would say that you have accuracy to 1. If it was 1 times 10 to the negative 4, you could say 10 to the negative 4 accuracy. But anything greater than 1, exactly 1 times 10 to the negative 4, you'd bump it up to 10 to the negative 3. That answer, Brian, how does that answer your questions? It's always 1 degree higher, unless it's exactly 1 times 10 to the negative 4, 1 times 10 to the negative 7, or something like that. Okay, cool. All right, everyone's good there? All right, let's do another one. Let's find the linearization for cosine x at x equals pi over 2 and approximate cosine of 1.71 without using our calculator, although we're going to end up using our calculator to determine the accuracy anyway. So first off, our function is cosine x. That's already given to us. We know what our center of approximation is. What's our center of approximation going to be? What's the a value? The a value we're going to use. Should be the value that we know, right? The value that we know is pi over 2. So we've got f of x is cosine x, and we've got a is pi over 2. And so our linearization function should be L of x is the cosine of x plus what's the derivative of cosine of x? That should be negative sine of x. And then times our x value minus pi over 2. Everybody good with that? So they should have a bad habit of just writing x's here, just because I'm so used to writing x's here. But those should be a's. Everybody good there? Yes, x is 1.71. Yeah, that's the x value we're going to use, 1.71, and the a's are the pi over 2. So I put in the a here, and these are supposed to be a's. Like I said, I have a bad habit of writing x's there because it's just what you normally write after a trig function. You end up writing cosine x. So now we're just going to plug in our value. So L of 1.71 ought to equal the cosine of pi over 2 minus the sine of pi over 2 times 1.71 minus pi over 2. And what's the cosine of pi over 2? No, cosine of pi over 2 should be 0, and the sine of pi over 2 should be 1. So this becomes -1 times this, or we can just flip the signs. So this ends up being pi over 2 minus 1.71. So that's the best approximation we can get for it. We might want to know what that approximately equals. So what does that come out to be approximately? Pi over 2 minus 1.71. Should get -0.139203673. That sound right? Yeah. Okay. And so that's our value that we're getting as our approximation for cosine of 1.71. And if we want to find the actual accuracy of it, we need to just take the absolute value of that minus the actual value of cosine of 1.71. So this is our approximation. And to find our accuracy, we'll do -0.139203673 minus the cosine of 1.71 inside of absolute values. And what does that come out to be? Hopefully I'm typing this all in right. I got 4.491 times 10 to the -4. That you guys got? Yeah. So that tells us what is the accuracy of this. It's within, go up 1 power to the -3rd. It's got 10 to the -3. Accuracy, again, it's within 1/1000th of the actual value. So not too bad. Any questions on that? Any issues with that? Everyone's good? All right. We'll keep moving on then. Actually, we're going to skip this for now. We'll do this for now. Okay. Part of this idea of linearization is using, so like we're using the tangent line to approximate the values of these functions. And there's one specific case when you have something like 1 plus x to the k power. And as the values of x get very, very small, very, very close to 0, 1 plus x to the k can be approximated using 1 plus kx. And we're going to see, when we get into series at the end of the year, we're going to see this pop back up, and we're going to use this idea quite a few times. So let's just see if real quickly we can use the idea that 1 plus x to the k is about 1 plus kx for very small values of x, and see if we can rewrite the 4 of these. This is sort of like our very, very basic introduction to series. It's not gonna make sense why it has to do with series yet, but you'll see it when we get there in quarter, I don't know, 3 or whatever it is. So what are we going to do with the cube root of 1 minus x? We should be able to rewrite this as 1 plus negative x to the 1/3 power. And anytime that you're applying this idea, 1 plus x to the k is approximately 1 plus kx, as long as this is just a function within here, it can still be applied. So even though this isn't just an x, even though it's a negative x, we can just replace the x here up in the kx with a negative x also. So what would this become? Yep, 1 minus 1/3 x. Easy enough. 1 minus 1/3 x. Any questions on that? What about part B? 1 over 1 minus x. How can we rewrite that? We could rewrite this as 1 plus negative x to what power? To the negative 1 power. And so what will that turn this into? Yep, just 1 plus x, right? It should be 1 and then plus our k value, which is negative 1, and then times our x value, our function, which is negative x. So the negatives will cancel out and just give us 1 plus x. Good or no? All right, what about C? How can I rewrite C? Hopefully just as 1 plus 5x to the 4th to the 1/2 power. So this is 1 plus u to the 1/2. So it should just be 1 plus our u value times our power. So 1 plus 5 has x to the 4th. Everybody good with that one? And then this last one, we should be able to rewrite it as what? 1 plus negative x squared being raised to the negative 1/2 power, which the negatives will end up canceling out. We should get 1 plus 1/2 x squared. 1 plus x squared over 2. Good or no? All right. Cool. So that's sort of just a little side note. We're going to use this idea a ton of times when we talk about power series and we do series. So just keep this in the back of your head for quarter 3. All right, let's talk about using a differential to approximate the value of a function. You should remember doing this, right? We're just going to treat the dy and the dx as if they are separate variables or separate pieces and separate them out. So if we know that dy dx is f prime of x, then for very small scales of x and y, the change in y, dy, should equal the derivative of our function times the change in x. This is just using a tangent line, still the linear approximation, to approximate how much a function changes, how much its y value changes, given a small change in the x value. Good? We remember doing this, hopefully? Even if you don't, it's pretty straightforward once we start doing it. So if we take the derivative of x to the fifth plus 37x, what does that give us? It should give us 5x to the fourth plus 37. So the change in y should be equal to the derivative evaluated at x equals 1 times our dx value, which will be 0.01. So we should have 5 times 1 to the fourth, 1 to the fourth plus 37 times 0.01. And so if our x value changes by about 0.01, then our y value should change by whatever that comes out to be. Looks like that is, oops, I don't know why I put that parenthesis there. There we go. That looks still terrible, but that's better now. What does that come out to be? .42. Yep. So if the x value changes by about 0.01, the y value changes by about 0.42. Good or no? All right, why don't you guys do this one on your own real quick, just to make sure you guys know what you're doing. Take like 30 seconds and do this one. Easy enough. You guys got this one done? Yeah. So you should have said dy is equal to 3 cosine 3x dx. And then you should have said dy, your change in y should be equal to 3 times the cosine of 3 pi. That's a really terrible s. 3 times the cosine of 3 pi times your change in x, which was negative 0.02. And the cosine of 3 pi is the same as the cosine of pi, which is negative 1. So that's negative 3 times negative 0.02, which is 0.06. That what you guys got? Perfect. I just needed to start boiling the water for my tea, so that's why I made you guys do that one on your own. Gotta boil it on the stove since my tea kettle, my nice electric tea kettle, is still sitting in my classroom. Very sad. I don't know what tea I'm gonna have, Darius. I'm just boiling the water right now. I haven't decided yet. Oh, sorry, not Darius. Darius backup. I don't know. I mean, I could, Adrian, but I also have, a stove at home, so I might as well just leave it there till I get to come back. I tried to leave as much there as I could. I could actually teach from my classroom if I wanted to, but since my wife doesn't work from home or is not able to work from home most of the time, I have to be home with the kids, and so I can't take them to my classroom according to our administration. So I have to be home. Otherwise, I'd just go sit in my classroom and make tea all day. It'd be great. All right, what are we going to do with this one? Same idea, right? Basically just like implicit differentiation. Now that there's y's on both sides, we could solve for y if we wanted to, but no real reason to. dx plus dy should equal, and then we'll have to use the product rule on the second piece of it there. So 2x dy plus 2y dx. And the only issue that we're going to have is we look for dy is what? What's the problem we're going to have? We don't actually have a value for y given to us, right? And so if we want to find that value for y, what do we need to do? Plug in our x value into our original equation, so we should end up with 2 plus y equals 4y, or what does that become? Y equals 2/3. So we'll put in a 2/3 value there. And let's see, what do we end up with there? We got 3 dy. If we bring that over there, maybe negative 3 dy. And then what do we have? We've got 4/3 of 0.05, and then minus 0.05. What's 4/3 of 0.05? I think that's, what does that come out to be? 1/15. So we got 1/15 minus 1/20, or dy equals, let's see. Okay, common denominator. Yeah, so negative 1/180. That sound good to everybody? That you guys got with your arithmetic? I just kind of did that quick in my head, so hopefully that's right. Somebody checking that? Somebody check that, make sure I didn't arithmetic wrong. Or is that arithmetic too complicated? All right, Molly thinks that it's right. That's 60 instead of a 70. Where do I have a 70? I don't even have a 70. Oh, that's a 20. There you go. That was a 20. Should be a 20. 0.05 is 1/20. All right, I'm going to trust Molly because she's trusting mine to be right. So, 1 second. All right, so now we're going to look at a couple of other different things. They're called relative change and percentage change. And so we're going to take a look at what happens if I, suppose I increase the radius of a circle from 5 to 5.1 meters. We want to figure out what's the approximate increase in the circle's area, and how does that relate to the actual area of the circle in the beginning. So about how much does it change as a relative amount, and how much does it change as a percentage. So we should be able to easily estimate the increase in the area. Even though we could find the exact change in the area, we're going to just estimate it because this is an easy function, but there are plenty of other more difficult functions where you might not be able to easily estimate it. So, or you might need to estimate it because you can't easily find it. So what formula do we need to use to figure out an increase in the area of a circle? We need the formula for the area of a circle, which is pi r squared, right? And so if we use a differential, that should tell us that the change in the area should equal about 2 pi r times the change in the radius. Everybody agree with that? Yeah, hopefully so. Okay. So then all we have to do is plug in the values that we've got. So we know that our original radius was 5. So our change in our area should be 2 pi times our original value of 5 times our dr, which is the change in our radius of 0.1, which tells us that the change in the area should be about what? It should be about pi, exactly. And we should probably put some units on that. Pi meters squared, yeah. So then the next question is, what's the relative change? And so our relative change is always defined as the amount that we think that it should be changing by our approximation of how much it changes. So that's f prime of a times dx. Or in our case, for this one, that's this value, this 2 pi r dr, right? It's just our differential of our function. So pi divided by the original area before the change. So this is our original value of the function. And so that'll just be pi divided by pi r squared, or pi divided by 25 pi. Obviously, the pi's cancel, we get 1/25th, or 0.04. So we'd say that the relative change is 0.04. And then if we want to know the percentage change in that, it's just the same thing times 100. So that would be a 4% change in the area. Good or no? And I'm waiting with you, but you're not saying anything else. Nick, the numerator is, it's the change, so the f prime of a is the f prime, it's the derivative evaluated that original value. So at the center of our approximation, right? F prime of 5 in this case, or a prime of 5, and then times the amount that it changes. So that's like it's like the second part of your linearization formula, right? F prime of a times the x minus a, sort of. I'm still waiting, Mahika. You said to wait. But you're not. You're good now? You sure? Everybody good? All right. All right, it's pretend time. Are you all ready? We're going to pretend that the Earth is a perfect sphere, even though we all know that's not true. We all know that the Earth is really flat, right? We're just going to pretend, for the sake of, fake science here, that the Earth is a perfect sphere. It's got a radius of 3,959.1 miles, plus or minus 0.1. Now, So we've measured the radius of the Earth to be 3,959 miles, but we think that perhaps we might have been off by 0.1 mile, either positively or negatively. And so we want to know what kind of effect that might have on a measurement of the surface area of the Earth. So how does missing the radius by 1/10 of a mile affect the surface area, or about how much does it affect it? So first off, what should we do? We should probably write an equation to represent the surface area of the Earth. How do we find the surface area of a perfect sphere? Surface area of a sphere is what? What's the surface area of a sphere? You should know that. There we go, 4 pi r squared. All right, so the surface area of a sphere is 4 pi r squared. And if we want to figure out about how much our surface area approximation will change if we miss the radius by a bit, we'll just use a differential, 8 pi r dr. And so if we want to know the actual amount that we're going to be off by, potentially, then we just need to plug these values in. 8 pi times our actual radius that we measured, 3,959, and then times our dr, which is 0.1. And so about how much are we off by? What does that come out to be? $9,950. Yeah. Okay. We'll say miles squared. Yeah. All right, fine. 0.052. 0.052. Good or no? What if I asked you what is the relative change then? The relative change should be that value that we just found, right? Our 8 pi r dr is 9,950.052 divided by what we would have actually gotten. No, the negative 0.1 would just be a minus, Molly. Right, I mean, that's not gonna, all that's gonna do is affect the sign. So, I mean, we could say that it's off by plus or minus 9,950, but we don't need to say the plus or minus. We can just say that it's off by 9,950.052. Okay, so then we're going to divide the 9,950.052 to find the relative change. What are we going to divide it by? By what our actual calculated surface area would be, which would be what? 4 pi times our radius squared. And so what do we get if we do that? .052 times 10 to the negative, right? Negative fifth power, right? So our relative change is 5.052 times 10 to the negative fifth, which means by what percent is our error? Our error, or our relative error percentage should be what? 5.052 times 10 to the negative 3%. So we're not really, even though it's 9,950 square miles, it's really only just it's 0.005% off. It's not very much in terms of how big of a thing that we've got. The percentage, remember, Nick, we're just multiplying by 100 for the percentage, so from negative fifth to negative third power. Percentage change. All right, back from there, percentage change. So our relative change is the proposed change divided by the original amount, but our percentage is that times 100. That should be relative. We'll just say percentage change. Good or no? Add 1 to the degree of the relative change. No, that's when we're talking about our error. That's a little bit different. So that's if we're talking about what is our error. And these are not errors. This is not how far off we are, but this is relative to how much it should have been. What did we get? So it's similar, but not exactly the same. All right. So what if we wanted to be within 1% of the true value of the surface area of a sphere? So if we wanted the actual surface area to be within 1% of its true value, how accurately should we measure the radius to find that surface area? It's sort of similar, but it's kind of less concrete numbers that we're working with the same basic concept of the last one. So we want the percentage change in the surface area to be 1%. So if the percentage change is 1%, what does that tell you about the relative change? Percentage change is 1%, that means that the relative change needs to be 0.01, right? And if we want a percentage change to be within 1%, that means it's less than or equal to 1%, which means our relative change needs to be less than or equal to 0.01. And what is relative change in surface area? Well, the relative change in surface area should come from S equals 4 pi r squared, and then finding ds, which is 8 pi r dr, and dividing that by the actual surface area, right? So our relative change should be 8 pi r dr divided by 4 pi r squared. Everybody good with that so far? Yeah, no, maybe. Okay, so simplifying that, pi's will cancel, some of our r's will cancel. We just end up with 2dr over r. And this is our relative change. We want our relative change to be less than or equal to 0.01, right? Which tells us that our dr value needs to be less than or equal to 0.01 r divided by 2, or less than or equal to 0.005 r. So in order for our surface area to be within 1% of its true value, we need to measure the radius so that our error, or dr, the amount that we're off by, is less than or equal to 0.005 of what the r actually is. Does that make sense? Any issues there? Good with that? And if we wanted to talk about that in terms of a percent, we could say it's 0.5% multiplied by 100 again, 0.5% of its true value. Good? All right, why don't you guys see if you can figure this one out. And K is a constant here. So take a minute and see if you can figure out how a 10% increase in the radius would affect the volume. And keep in mind, like I said, K is a constant. So take a minute or maybe 2 minutes to try and figure that out. All right, I'm just going to put this up here because I forgot to restart the recording so that people can see it in the lecture. This is what we did, blah, blah, blah. This is the other problem that we did. You can just pause the video if you need to look at it, blah, blah, blah. The end.